Good morning. We are very honored to welcome here Professors Lizy John and Eugene John is one of extra PESC seminars. They are both from the University of Texas. Professor Lizy from San Antonio, from Austin, and Professor Eugene from UT at San Antonio. Professor Lizy is a Truchard Foundation Chair in Engineering at the University of Texas at Austin. She received her PhD in Computer Engineering from Pennsylvania State University, and her research interests include workload characterization, performance evaluation, memory systems, reconfigurable architectures, and high-performance architectures for emerging workloads. She is the recipient of many awards, including Joe J. King Professional Engineering Achievement Award 2023, the Pennsylvania State University Outstanding Engineering Alumnus Award 2011, the NSF Career Award, UT Austin Engineering Foundation Faculty Award, Halliburton Brown and Root Engineering Foundation Young Faculty Award, the University of Texas Alumni Association Texas Access, Teaching Award, and etc. Because there are so many awards for this gentle person here. And it's also, I'm very proud because she's a woman and in a very, very masculine area. And so she's a very tough cookie. Also, that we catch up. She has co-authored books on digital design, systems design using VHL, VHDL, Cengage Publishers, 2007, 2017. Also a book on digital systems design using Verilog, Cengage Publishers, 2014, and has edited 4 books, including a book on computer performance evaluation and benchmarking. She holds 16 US patents and is an IEEE Fellow, ACM Fellow, Fellow of AAAS, and Fellow of the National Academy of Inventors. 9. So please, she will talk about machine learning for performance and power modeling. Prediction.
Thank you, Priscilla. That was an elaborate introduction. I think I was lazy I thought I'll just cut and paste something and send it and you will shorten it.
No, we're not going to do that.
But thank you so much.
It's good.
But I'm very happy to be here. We have been talking, collaborating with Priscilla and Felipe and, some of the students for some time. And it is such a great pleasure to be here and meet in person. And I am primarily a computer architecture person. And I do hardware for whatever needs to be run on hardware. So at different times, it's different things. In recent years, it has been machine learning. But over the years, so this gives probably a picture of the kinds of stuff I have worked on in the past. It's, microarchitecture or architectural techniques for some kind of workloads. That's, different times it has been different workloads, Java, multimedia, databases, electronic commerce, now machine learning. So I have done a lot of performance evaluation because in order to design hardware, design becomes easy once you know what is to be designed. And what is to be designed, you cannot make that decision just intuitively anymore. You could do that 30 years ago, but now workloads are so complex, architectures are so complex, it's not easy for, if you are smart, you think, oh, I can just tell how that workload will work on that architecture. Those times are gone. It was true 30 years ago, but not anymore. And once you start designing or evaluating, you see it's so complicated. It's not easy to evaluate anything and say this is better than that or this is this much better than that. So I have gone into a lot of performance evaluation. And so architecture and performance evaluation have been the topics that I worked on for, the past many years. I would like to thank my wonderful graduate students who did the research that I'm talking about, and also the various agencies that have funded the research. And so I'm going to pick a few things to talk, and they are going to focus on performance and power evaluation or modeling of systems. And these examples use or illustrate the use of machine learning to do that performance and power modeling. But primarily, this is all for good hardware design at the end. So the very first example, so 3 examples. The first one is in architecture, in computer architecture, we use simulators and models to decide, should we do things this way or that way or that way. So, but many of these simulators have a lot of error in them. So the first example is how we can use machine learning in order to calibrate power models and make them better, more accurate. The second example is these models and simulators are usually very slow. Slow means 10,000 or 100,000 times slower than actual hardware. So you cannot really simulate full applications on any of these simulators because it might take a month to simulate one configuration of that architecture. So if you want to simulate to decide which one is better, it takes 6 months. And then you found out that there was a bug and you have to fix everything and repeat everything. And graduate students spend 5 years, 6 years, 8 years just running these simulators. And by the end of 8 years, what they start, everything is outdated. So you have to redo things. So is it possible to run workloads on real machines so they are faster and use the correlation between this machine and something you are going to decide and use machine learning to predict the performance? So you don't use simulators entirely to predict, but I'll talk a little bit about, you do still use simulators for some purpose, so cross-platform prediction. And if there is time, I will also go into a third example and about stress benchmarks or stress marks. So how much time should I use? 30 minutes?
As much as you can. Relax.
Okay. So the first example, this one is about power modeling. And MUTPath is a very popular power modeling tool that industry as well as academia uses in computer architecture to estimate the power of architectures or building blocks. And if blue is what the simulator tells, or this is not entirely simulation, it has some analytical modeling and some simulation. If blue is the power given by MUTPath, if you actually make hardware like that, you often see that's not really true. It was all wrong, and the red line is what you actually find. So if you have many examples or a few examples like that, can you find how wrong the simulator is? And so you still use MUTPath, but when you get the blue point, you use that correlation to come to the red. And so eventually we can be like this. So we use a simulator or model which is wrong, but use the machine learning to calibrate it or bring down the error. So that's the first example. And this is done using regression. It didn't need anything way too complicated. It doesn't need big data either. It only needs like 20 to 30 data points are sufficient to find that error to be able to calibrate. And so the original MUCPAD, the tool has branch predictors, it has TLBs, instruction cache, data cache, models for all of those, and it adds up all of those things. It also uses a simulator to run a workload to find out how many branch predictions did you do, how many cache accesses did you do. So it gets all kinds of statistics about the workload here, feed it into MUCPAD, it gets the numbers. But so there is, in each of the numbers it used, there is some error. So can we determine the coefficients to correct those, the errors in the coefficients and correct them so that instead of the original coefficients, you use some of these corrected coefficients and you predict the power. That's the idea there. And yes, it can be done. And we did this using, if you use entirely simulation, even to prove our thing is correct, you won't be able to validate it. So we use ARM hardware and the ARM Odroid board and the DS5 system that ARM provides in order to get the true numbers to validate things. And it is done using performance monitoring counters, which are abundant in all microprocessors now. And so these are the types of metrics you measure, or so these are the features basically made use of in the model. And so you can measure all kinds of things, hundreds of performance monitoring counters are available on systems. You can't measure all 100 at the same time. You can measure 4 or 8 or something. So you run a few experiments and you can measure the kinds of metrics you are interested in, the features to feed into your model. And the correction factors we found, you needed basically additive as well as multiplicative correction to the original factors. And the model, the regression that was needed to solve this was, it had to be a non-negative least square error solver. We used the least square error solver first. That didn't work, but the non-negative least square error solver did work. And with that, we basically could bring, the yellow is the original error between the model and if we tried the same configuration on actual hardware. And once calibrated, the green, and we had 2 different kinds of models, but they're not very different. The 2 greens are 2 slightly different models for the correction. So, and if there are questions, feel free to ask me.
Do you want now or after?
Either way is okay.
She's leading. I'm the director. I'm only make sure the transmission can join.
Feel free to interrupt. And also, this is not only the average power at the end or the total. So some positive and negative errors cancel and you try to get good numbers. This is actually, we can do it in a time varying way and over small intervals keep measuring, and you can see that when the actual power goes, the model also basically tracks very well and we're able to reduce the error. So this was interesting work and very encouraging, and that's the first example. The second example is a little bit more complicated. In the sense, here we are going to use maybe real hardware and a simulator. So there are 2 platforms. One is faster. So the simulator is slower. So we do need a simulator because we don't have this new architecture that we are envisioning. So you make a simulator, but that simulator is very slow. So you can't run really entire applications, end-to-end things with also maybe some applications need Java or something, which the simulator doesn't handle it. So simulator can only do certain things. So is it possible to have a training set, a few small programs, which will run on the simulator and it will finish relatively quicker? So run these training programs on both the platforms, the real faster machine, but previous generation, and the new machine in your mind, but only a simulator, which is very slow. So run both the things, and the model is going to capture the correlation between the 2. The real machine gave these feature vectors and the simulator gave those feature vectors, but it's the same workload, you have paired features, and the statistical model can basically extract the relationship between the two because it's the same workload, and you have that model here. Once you have the model, when you have a new application, which is bigger, which may not even run on the simulator, but now we can run it on this actual machine and it is pretty fast. You run it on this, you get these features, but we know the model can extract this for the other. That's the idea. So cross-platform prediction and performance and power. You can possibly do it for anything you want to measure as long as you are able to capture the correlation. And so this one, I think I kind of explained when all you would need it. There are a few more use cases, but in the interest of time, let me just go forward. And the training set we used was from the ACM programming contest database. So there are all kinds of algorithms, different domains, codes are written by, it's hopefully pretty good codes because it is in the competition and the winning ones are the good ones. So we used, about 150 programs from there. But each of those programs can be run with many inputs. So you can generate more data like that. Also, you are not generating only one data from one program running one input, but you can take data as you run it. You can do it at, the first, the simple example, first millisecond, next millisecond, next millisecond, or whatever time granular. Or in the sense of a program, you can do it at basic block level. So you use 1,000 basic blocks, the next 1,000, the next 1,000, the next 1,000, so you can have a lot of data. So this actually gives a lot of data, although it's only 150 programs, and you are able to train the model in order to extract that correlation and create a model that captures that relationship. And we used performance monitoring counters because you can run real programs, it is fast. And we used the Intel and AMD machines in order to train our model. And we are predicting, whatever we are predicting, we want to be able to, we used an ARM platform to predict. So basically, first we train on Intel, predict on ARM, train on AMD, predict on ARM. That's what we did. And Intel, there were more counters. AMD, that particular machine we were using did not have as many performance counters. And we show that it doesn't really affect as long as you are getting essential features. Okay. So when we predict the performance of an ARM processor, this one is performance, so cycles. We run the program on an Intel and predict what would be the number of cycles taken on the ARM. That is actually the third bar. The first one is, this is the actual. This is what is predicted based on training from Intel. The second bar is if you trained on AMD and predicted ARM. The errors are shown in the red and the green. So the red means the error trained on Intel predicting ARM. Green is trained on AMD predicting ARM. And this is phenomenally good. Okay.
It's great.
It's unbelievably good. But we did not reach here very quickly. It took about 2 years of work to get here. The first models had 60-70% error. Okay. So it doesn't, this working at the end does not reduce the importance or the difficulty of the work. So in the beginning, we were looking at the larger program as a whole. We would imagine plus and minus errors, cancel, and we should be able to do it. No, it wasn't working. We had to go into the fine-grained correlation in order to make things work. Also, the particular model that was used, we used different kinds of regression, piecewise, linear, regression constrained. Lasso was what worked at the end. None of the others that gave as good accuracy as this. So it took a while to reach here. On performance, it is phenomenally accurate, less than 5% error or 2%, 3% error. Power, the error is slightly more, but still very good. However, for some of the difference, if you did not do the granularity, the model is sensitive to the granularity. And if you do very low granularity, you have to work harder. You have to, generate more data. There is more to do there. And the instrumentation also has to be more accurate because it's easier to obtain accurate metrics over the whole thing. If you were to instrument that 1,000 basic blocks, there is a lot of noise, and noise affects you more. So there were challenges in doing this, but the granularity is important. At the end, but with the fine grain, over 5,000 basic block tracking, we can see that our model follows the actual very correctly. When things are fluctuating, our model is predicting that it is happening for both power and performance. Okay, so that is the second example. Any questions? Yes.
Not a question, but okay. How it was for you when you advise the students, when you realized that you were able to get that excellent prediction without, if I understand correctly, I did not read the paper, needing details about the microarchitecture you are simulating, because that's a huge part. I don't know if the students grasp that, because if sometimes you can build an AI model, but as we know, insights of the microarchitecture that we are trying to predict about. So that should happen. The group was able to do that, to extract that only from execution of experiments, only from the result, the features that we have on the performance counters. That was really fun to see the results.
So on the previous one, this work, the student was a computer architecture student with good knowledge of hardware and power and all that stuff. On this one, this student was not even a computer architecture student. This student was a student from the software engineering side of the department. He was interested in machine learning, and he, I guess, somehow said, I can use machine learning to, some lab mate, you are struggling to do this with simulation. I can use machine learning and tell you the answer. So he basically does not know anything about hardware. He did not take any class from me. He went and took all the machine learning classes all over the university. Whatever class was offered, he took all of them. He did not take hardware classes. He did not understand hardware either. So he believed he can do this problem that his friends were trying to solve with detailed simulation. He said, I can do it without the knowledge. So his theory here, or his argument was, as long as he needed someone to tell him what vector should he measure. Because he doesn't know TLBs, he doesn't know branch, he didn't know anything about hardware. So we had to tell him, hey, you shouldn't skip, you should make sure you measure this because that's an important feature. Okay. So the advice was that he needed was on what metrics he should measure. But so it's kind of interesting that someone who has no hardware knowledge is able to use machine learning to do a good job on something. We, with our domain knowledge, would create detailed models and still fail to predict correctly. Yeah. Or we have a huge simulator that can run for years. And
for us, I think that the result is great, as I said. But what tells us is we are leaking a lot of information on the microarchitecture through the benchmarks.
Yes.
Maybe, and we should start to thinking more about that because it can help the research a lot.
There is a lot of information out there, side channel links, you can say. Okay. So all of these things and more are there. That's enough for someone. Okay. They don't need to know really how it's done. That's the point.
As I said,
so it's interesting.
Calibrate exists. You said this is important. It is important, but you don't need to understand how I implemented the details and just know that it's great.
This is just like some coffee shop near the university said they can predict the GPA of the students who come there. They don't need to know anything, just by their coffee habits and how much time they spend. They could measure, they could predict pretty accurately the GPA of the students.
I'm sending you an email after the talk. I want to read this paper because it's really interesting.
Okay. Yeah, so there is a lot of correlation. That's the thing.
Yes.
There are metrics that are telling it out, and we could use it. I don't know how I'm doing on time. I'll quickly go to the third one. Is that right?
Yes,
Yes,
great.
Okay. So this one is about hardware designers, especially regarding power and thermals, are often worried that there may be some workload that just drives the hardware to a point where it melts or too much power is consumed or too much temperature increases. So okay, we could say they should design something, even if the temperature came up to here, it should work, or they should, do something. But if you start designing for a very high margin and saying something there, the amount of current corresponding to that should come on the wires is so high, you have to over-design the power delivery system. So if you want to design a reasonable power delivery system, you kind of want to know how far can someone drive software to go the power up or temperature up. So they want what is called a stress mark in order to compute that. And what we used is, we basically said we can automatically come up with these stress marks. In companies, what they do is someone with intimate knowledge of the hardware and assembly language program, they come up with a sequence of instructions. If I ran floating point multiplication with 64 bits with these types of numbers in a row, that power will go up. Or, some unit that takes a lot of power, they drive that unit high. Somebody had to know the hardware. They think all day and night, how do I, and will somebody still drive it more than what I thought it would, right? It is a human being just doing it. So this is automatic. Again, this doesn't need the domain knowledge. You can do it with machine learning, figure it out blindly. That's the purpose here. So here the way it was done is, in other research, we had a little bit of research where we characterize the workload, take a real workload, and then spit out a proxy which has the same performance and power characteristics as the original workload. The reason it was done, it's important. Sometimes the workload is proprietary. We don't want to give it to anybody to evaluate. I'll give the proxy. Or the workload is huge and I can't handle the huge workload. I'll give out a proxy which is miniaturized or something like that. So we use that framework. And using that framework, instead of making that proxy to match the original workload, we drive the proxy to crazy levels of some metrics that the power is very high. We use a genetic algorithm. So we make one proxy, feed it to the genetic algorithm, a couple of proxies, and then let it do the genetic mutations and cross, and then create. So features are important. We use the same kind of features we used in previous cases. We create a synthetic proxy. It's a bunch of basic blocks with no meaningful instructions, but only the performance and power things have to match. You don't need any functionality. And with that proxy, we drive it to extreme powers using the genetic algorithm. And we were basically able to, we could create proxies, and we could create proxies to make extreme stress marks. And we did the stress mark thing for x86. In the x86 world, these are some publicly available stress marks for some of the earlier x86s. They are all assembly language programs. There is the best C program if you want to drive an architecture crazy is Mersenne Prime Generation. That's a C program that takes very high power on any architecture we have tried. And there is nothing else that takes as much power at the high level language. But people can create these assembly language programs. So our objective was to beat even all the assembly language programs and do it automatically without knowing anything about the architecture. So we studied all the existing ones, and we use the genetic algorithm and the proxy mechanism. So the genetic algorithm did its crossover and mutations and all that. No matter where you start from random starting point, this is the M prime. The genetic algorithm can overtake it after a few iterations. And we were able to basically come up with very high power stress marks. And we did it on multiple platforms, multiple ISAs, and we also did it on x86 hardware. On this one, there was this assembly language program that was done by people who designed the machine and knew so much everything about the machine. So we didn't beat it by way too much. The last bar is corresponding to this hardware. We could beat it with others well, but this particular one, someone who knew everything about the hardware, we could still beat it by some, even if small margin. And we actually talked to that person who did the one. He said he was happy to see we didn't beat him by too much. He said, I worry every night that what I made is not good and someone may create something. So he wants to use our thing or something like that. So you know that, oh, how far can it go if somebody automatically tried something? So it was pretty good. And a few more examples, but I think I'll stop there. So there are many ways machine learning can be used in performance evaluation for hardware design and for evaluating performance as well as power. And we can use the same philosophy to measure other objective metrics of interest. All right, thank you.
Questions?
You guys have no idea what she just showed.
Yeah.
Because no, of course it is. As she said, someone don't have experience, he got these good results. Of course, she has experience. She was advising a student. However, it also means that if she has the experience and she used this type of software to guide her knowledge, she'll go far or faster than is feasible. Just like the researcher asked her for the code, because even if we build something, we are not able to fully grasp all of the possible connections. We think some are important, some we miss.
Yeah.
And that in them, I think machine learning has for at least us that are computer architecture can help us a lot. If we are humble enough to understand that I'm not able to understand all the correlations, some may appear that I never intend to be there, and I can use it to guide my research, to guide my work. So, Lizy, thank you for the talk.
I have a question.
Of course, please no.
I'm just standing here.
For machine looking for the architecture is.
Do you have? Did you work on feature selection?
This work was actually done a few years ago, before I started doing so much more in machine learning.
Mm-hmm.
So at that point, what the features we selected is basically from the hardware point of view. We didn't think so much about what other features may be there or anything like that. We just thought, clearly is important. We need to know what's in the cache. We need to know this. We need to know that. But now I may go back and maybe there is something. I hope we got all the major features, but perhaps there may be other things. And also in the light of multiple cores, multiple things, there may be features related to sharing of data. There may be features related to maybe network or other communication, so there may be other things. At that point, probably we were more naive in terms of machine learning sort of way of thinking about it.
So if you automatize the feature selection as well,
you are gonna give a nightmare for the guy that create burn 7, because he's just like, okay, now I have another issue.
Yeah, at that time we were trying using our hardware domain knowledge, give it to this person who doesn't have that. But we didn't have the same machine learning insights. And automation for the feature selection is another thing.
At least to see how clever the machine can get.
No,
it doesn't.
Actually, it's a little bit worse because we know that the companies do put something on the processor that they don't tell us. Some shared components there inside of. We know about most of the bus, but there are other shared components, and sometimes appear some patents, another only when something break. Feature selection may find those, not those components, but the correlations because of those components. So that can break really fast. That's why I say that would bring nightmare for the guy who wants to use the software.
As you were mentioning, when you mentioned the coffee shop, I was wondering if other applications, like domain agnostic, machine learning method, this method could be applied to other domains.
I think the thing that computer architecture brings is that we have a lot of samples. It really generates samples really fast. We say 1,000 time event. For us, this means that every milliseconds happening.
Mm-hmm.
So that's why I think it's so fast, the result. But as you said, it's probably be able to apply it in different domains. Computer architecture is a really great place to test it because we just generate too much samples in a short amount of time. At least Lizy did the work.
So I think Professor Lizy from
let me just remove it. I have to train more people to control the everything, but now it's only me.
And now it's also a pleasure to welcome Professor Eugene John, also from the University of Texas, in this case at San Antonio. He received his PhD in electrical engineering from Pennsylvania State University and is currently a professor in the Department of Electrical and Computer Engineering at the University of Texas at San Antonio. His research interests include another very important subject, which is energy efficient computing, ultra-low energy computing for implantable cardiac devices, hardware architectures for machine learning and artificial intelligence, computer performance analysis, power-aware and secure systems, and low-power integrated circuits and systems. He has over 160 publications and 7 US patents. He was inducted into the National Academy of Inventors in 2022, and he is a recipient of the University of Texas System Regents Outstanding Teaching Award. He served as an associate editor for IEEE Transactions on Sustainable Computing. If we had known that, we would seek some advice before. And is currently serving as an associate editor for the ACM Computer Science. Thank you very much. His talk will be about ultra-low energy computation methods for implantable cardiac devices.
Thank you, Christina, for a wonderful introduction. Bon dia, good morning. Well, Friday, and you are here to listen to back-to-back talks. So I will make sure that I will make it very simple, very quick. So I'm not going to go to the minute details. I will explain the high level why we are doing this, what the purpose of this, and high level solutions. And if you are interested about knowing this in details, I have put the papers that we published and the patents we received based on this research. So we can refer to that. Okay, so this. Okay, this is my presentation outline. I will keep going. Before I start, a little bit pacemaker trivia. But yeah, I look around, you're all very young, you don't need pacemakers. So at some point in time, God forbid, you may need one. So pacemaker is a device. If your heart, well, your heart has to beat, the blood has to flow. So if the heart doesn't beat the right way, well, then they take a step back. If you ask a cardiologist, they will say there are two things in a heart: a pumping system and the electrical system. Pumping means blood has to flow. Your blood vessels should not be blocked. The other thing is the electrical system, the electrical signals that makes the heart to beat. Okay, so pacemaker is a device that intervenes if something goes wrong with your electrical system, that heart is not beating the right way. Well, now the machine takes over and starts make the heart beat the right way. So how did it happen? This is, well, pacemaker has been, people have been thinking about pacemaker for a long time. This is a Swedish electrical engineer received the world's first implanted heart pacemaker in 1958. When we say that he is the one who received the first implantable, means completely implanted. That is, everything is inside. Before that, there was a pacemaker outside, the battery, pacemaker inside, battery outside. So we had to carry with the battery around. So you can see it's very inconvenient, right? So this is the time, this is the first version. Everything is inside. And there was no these days in US, in every country, if you had to do any medical thing, you had to do lots of studies, there was nothing. So there was one doctor, a cardiologist, and an electrical engineer. They kind of made a pacemaker. And this gentleman has having lots of issues. Heart is not beating right. And his wife went and talked to those two people and convinced, please implant this into my husband. The husband said, well, I'm not feeling well. Whatever, I will take it. So the doctor and the engineer, they were a little reluctant, but she convinced, well, please do it. And they did it. And there's Dr. Seni is the heart surgeon, and Dr. Enquist is the electrical engineer who made it. And unfortunately, within 8 hours of the operation, the pacemaker failed. But there was an electrical engineer, so he made a backup one. So they put the backup one back, and it worked. Over the period of his entire life, he has to undergo pacemaker 30 times. He has to go through the replace the pacemaker or fix pacemaker, but he outlived the surgeon and then and then he lived all the way up to 86, the age of 86. 86 is pretty decent age.
Yeah.
So, and he by trade, he's an electrical engineer who fixes the electrical properties of the ship. So the electrical systems in the ships, so he is the one who fixes that. So he traveled around the world. He had a productive, nice life. So that's a little trivia. Now let's go back to human heart. Well, we all have a heart, right? Well, figuratively and physically. So now there are 4 chambers, 2 upper chambers, 2 bottom chambers. The upper chamber is atrium, this ventricles. So your upper right chamber receives all the oxygen depleted blood. When it shrinks, that blood goes to the lobe chamber on the lower right. So right ventricle. From there, blood goes to your lungs. From the lungs, that's the process, and oxygen-rich blood comes to your right atrium, the upper left atrium, upper chamber. From there, it goes to lower ventricle. From lower ventricle, blood goes all over your body. These actions has to happen in a synchronized way. How does that happen? That's where the electrical things come into picture. We are all electrical engineers now, right? So these are the electrical system. So this is kind of conductive node, and this is called sinoatrial node, SA node. That is the little thing that produces the signals that it needs. And this is the only thing in a human body that is not controlled by the brain. Everything else is controlled by the brain. So even if your brain is even if your brain dead, the heart will still beat because SA node keeps beating. Okay? From SA node, let me go. This is the electrical system overlaid on the heart. This is just the conductive fibers. From there, these are for the atrial stimulation, and this is AV node. From here to here, there's a little delay. Delay is introduced. That means atriums, then ventricle. So something goes wrong. So for whatever reason, if this gets damaged, well, then the rest of the heart doesn't work. You all see what I'm saying, okay? So that is, now what is a heart arrhythmia? Heart arrhythmia, that means your heart is not beating right. So when the electrical signal is not properly propagated, something is wrong. And it is a heart arrhythmia. There are, according to arrhythmia handbook, there are 94 different kinds of arrhythmia. So each person may have a different kind of arrhythmia. So the doctor has to find out what kind of arrhythmia is this person having and which chamber is having the problem. There are 4 chambers, so we have to find that out. So a heart arrhythmia may feel like a fluttering, pounding, or raising the heartbeat. Different people feel different ways, so something is wrong. So in general, arrhythmias are grouped by heart rate. Sometimes heart beats very fast. That's called tachycardia. Sometimes heart beats slow, bradycardia. So let me make a comment on that. The heart rate is less than 60 beats a minute, bradycardia. If you go measure and your heart rate is 55, no, you're not having a cardiac arrhythmia. So if you're very, very healthy, your heartbeat is very low. Do you all know Michael Jordan?
Yeah.
Okay. So he is one of the best basketball players ever. I'm not going to talk about that. But what this is, his physical condition was extremely good. He took care of his body. So his rest heartbeat, it was around 45, 48. So that's all. That means his heart needs to be only that much to get the blood around. So if sometimes you feel, oh, wait, I have to do something. No, you have to go to the doctor. Yeah. The six most common arrhythmia types are AV fibrillation, atrial flutter, supraventricular tachycardia, ventricular fibrillation, bradycardia. So this is I just put it. As I said, there are 94 different kinds. Only around 12 are most common. Some of them are very, very rare, but it has been found in certain people, so it is recorded. Well, I'm not going to go this. So this again, just explaining what each one of these. Now, how do you treat? You can treat using medicine, electrical cardioversion, catheter ablation, pacemaker, implantable cardio defibrillator, ICD, and pacemaker. There's a slight difference. So some people needs only a pacing. That means the signal is not there. The device will give the signal. In sometimes, for example, the heartbeat beats very fast. We need to slow it down. What we have is electrical shock. So that the defibrillate. So certain pacemakers has the capacity to give the shock. So not again will every pacemaker will have that? No, depending on the disease. Some people need that shock. So that's the difference between ICD and pacemaker. So this is, excuse me. So this is the normal electrocardiogram. This is the bradycardia effect ECG. The cardiac pacemaker is an extremely resource-constrained embedded system. That statement is from an electrical engineering point of view. So when you say extremely resource-constrained means, you put a battery. So your pacemaker goes here. I have a couple of slides later that I will show that. That's inside your body, right, on the chest. So once it is inside, you cannot recharge. And the battery is there. Typically, the battery lasts between 7 to 10 years, depending on the severity of your business. Sometimes now we can ask, can you recharge? First of all, there are no terminals coming out. So, but now we have seen charging the phone by putting on a pad, right? There's no connection, but still you can charge your phone. There are some devices like that. Can we charge like that? No. The reason for that is, if you have you seen this? Your some cell phones you just put on a back.
Yes. Yeah.
So now you
For
can
preparation.
just why can't you do the same thing with this? The problem with that is this is between the pad and the pacemaker and the battery, the skin. The skin will absorb all the electromagnetic waves. So that skin prohibits. I don't want to use the word prohibit. Kind of make it difficult for you to recharge the battery. Well, some research is been going on about recharging the battery. It is taking its time. It is not there yet. So we cannot recharge the battery. We had to. All pacemakers have an ability to. They will. It communicates wirelessly, so you can read. So it will tell, hey, I'm going to die. That means my only 20% charge left. Normally around 20% they replace. So you don't want to take a chance. So how do you replace it? And the operation. And it's a full anesthesia operation. So it's some doctors call it a minor minor surgical procedure, but some people bark at it. No, it's not minor. For example, I wrote in one of my proposal, minor surgical procedure. One reviewer said, is not a minor surgical procedure. But I got funded. So,
Minor for them is the
yeah.
robotic only.
Yeah, so it depends on, it's not, you're under full anesthesia. So you have to, and it's hermetically sealed. So that means you cannot replace the battery. You have to replace the whole thing. So, and the pacemakers are very expensive. It could be between $6,000 to $30,000 depending on what pacemaker we are talking about. Let me take a quick sip. So the whole idea of the research is to find the circuits that takes less power but does the same thing. So what that will do is that will increase your frequency of operation. So you all got the idea, right? What we are trying to do. Okay. So this research focus is on low power implantable cardiac-based pacemaker technology. So the pacemaker still has to do its job because it's life critical machine it's doing, but using less power. So this is your typical ECG. So sometimes you will say EKG is the same thing. Cardio in German you write K. So normally it has 7 to 10 years. Well, let me go to the next slide. So this is where it is kind of implanted. This is where it goes. This is inside the body. And you make a hole here, then the leads go through that blood vessel into the heart. So in this case, right ventricle and right atrium. So they have put this. Then this is another new session. If you are free to ask questions, whatever you have. Okay. So that's the illustration, and this is actual X-ray. So the patient implanted pacemaker. Okay, let me explain this. This is the 2 pulses. So this is the P wave. This is where the atriums shrink. Now, after a little delay, then this is QRS complex. That's when the ventricles shrink. Then this is ventricle rest period. This is not well defined. Some people have that, some people don't have it. So any deviation from this, you have some problem. So that's how you detect whether you are having arrhythmia or not. So I will show you another bunch of slides coming later on. So okay, here it is. So this is your atrial fibrillation. This is atrial tachycardia, ventricular tachycardia, ventricular fibrillation. Okay. We are not worried about that. The cardiologist as well. The moment he sees, they know what it is and they will proceed from there. Evolution of pacemaker technology says that initially in Sweden, 1958, there was nothing, right? They just made one and put it. Then it took a long time. Now we all drive fancy cars. Have you ever thought about? Have you seen the picture of the very first car?
The very first?
The very first car initially.
No,
the early
no.
days. There's no roof. The steering was in the middle. There's no windshield.
Mhm.
So what I'm trying to say is, it took over 100 years to reach this point. Now everything
Yeah,
is you don't even have to drive. You sit there. So this is 1958. This is 2030. So it took a while. So now I wanted to show you this. This is how small some pacemaker, not all, some can be this small. So these kind of pacemakers, they don't.
No, I was just
just saying
amazed.
it's-
It's leadless.
Yeah, so
That's
leadless.
bad for your
That means
It's,
so
it
you
goes
don't
inside.
have these leads. That's
It's
what I'm
inside,
saying.
okay,
directly
okay,
inside the.
uh-huh.
Yeah, then exactly.
Ah,
It goes
okay.
Then what
inside
is-
the heart. So then I said,
Oh,
how do you measure it? Or how do you operate? Here it is. You put it inside the heart. Just put it there. That's it. So it has. Yeah, I'm showing the technology has advanced quite a bit. Okay. So now, connected smart implantable cardiac rhythm. This is where we started working on our project. Currently, we have all the technologies to implement this, but if a patient who is implanted with a pacemaker or an ICD, so the doctor has once in a while he or she has to go to the doctor's office. What they put is a kind of a van, something like this, and the other end goes to a computer. So inductively they can read what is inside. So that's how they find out how much battery left, how the the pacemaker stores every single beat. So that's so the doctor can see what happened for the last 3 months or last 6 months, then find out everything is fine or not fine and so on. Now, the current thinking is we have low Bluetooth connectivity and we have a cell phone. Your cell phone is connected to your heart pacemaker, and cell phone can be connected to any place and that can be recharged, right? So cell phone can be connected to doctor's cell phone and hospital network. Something goes wrong, so without the patient knowing, it can automatically alert the hospital or the doctor, and immediately the doctors can take preventive action. Sometimes doctors periodically reset the parameters of pacemaker. Resetting the parameters means how often should the treatment should be done. Typically, the amplitude of the pulse and the period. So that depends on lots of things. So this can be done, but if you don't have it yet. Now, the problem with this is that you have put anytime you have a transmitter inside, that takes lots of power. And in your cell phone, the most energy is used to send the call out. The receiving takes only less power. So we have this kind of, we want to have such a thing, but can we do it? Yes. Now it will drain the battery quickly. So instead of 7 to 10 years now, we may become to 3 to 4. We don't know. So I'm just giving some numbers. So without compromising on the longevity of the battery, how can we do this? So that's the objective. As I said, it's an extremely power constrained device.
I
Yes.
just a quick question. When they go to the doctor to read whatever is stored in the pacemaker, does it consume battery for this reading, or
Yes, it
the reader is
Well,
able to read?
that's very less. This is
Okay.
an inductive thing. So
Okay.
I collaborate with an electrophysiologist. So I have gone to his office and he showed me how to do this patient sister. It's very less,
Okay.
not that much power is consumed. Okay. So as I said earlier, extremely power constrained embedded system. That's a pacemaker. So this is powered by typically 2.8 volt battery. This is now other thing you can have is you can make bigger battery. Well, it's a pacemaker, right? So some of the pacemakers like this, but we are going the other way. So that's another. It's not a good option. And it has to have lasting, it should be long lasting. Excuse me. So this is design abstraction. I will come to that later on. Now, as I said, there are 94 different kinds of arrhythmia. The first thing is to find out what kind of arrhythmia you have, the patient is having. So that's the mainly by processing the ECG. It's not mainly, it is by processing electrical ECG. So this is digital detection method for ECG classification. Fourier transform is one of the most popular thing. So you have first you go through the incoming ECG is converted into digital signal. So AD, analog to digital conversion. Then you do the FFT and go from there.
Eugene, just a comment. One of the things Priscilla asked about, I think that one of the things it's not that doesn't consume a lot, but the frequency the doctor go to extract data is not as much as we can do with Bluetooth and things like that, right? We are talking about reducing the intervals to get the data in order, so that we, even if we are able to build something that consume does not consume a lot of energy, if we want to do higher frequency to get the data, we end up consuming through those samples much more than in the past, when maybe one a year or twice a year.
With my interaction with my collaborators, he never, his name is Manoj Pandey, so Manoj never mentioned about energy being used in reading the device.
No, I was just meant because the frequency we go to the doctor is never as much as we are having.
Exactly. It's maybe 6 months or 1 year. Again, if the patient is not having any issue, maybe
2 to 3 years. Then
unless the patient is having some issues, we don't even see.
Usually, because of funding the medical area, we know they start going in the beginning. It's shorter span of time. Then once a year, everything's great. Like 5 years, come back in 2 years and on.
As long as the patient is
well,
not having any complaints,
you can delay the visit, so you end up not using the transmission. That's it. So it's something that we need to keep in mind. That's not only building the resource that's consume less energy, but we are in the future we would like probably to get that data more active, more frequently, in that even a really low energy design will still end up consuming a lot of the energy because of the amount of samples we would like to have. Sorry to interrupt. Is that because it's really interesting to think about it.
Students, I don't want this to be a monologue. So I teach subjects in grad class and undergrad class. You go to undergrad class, they are all enthusiastic, lots of questions. I keep talking, so we have
because it's
very nice conversation. I go to grad class, they are all. No, you are supposed to be asking more questions than undergraduate students. Okay?
They are very quiet.
They're gonna.
I didn't mean you.
No, a few of them gonna. A few of them are gonna die in the lab. Yes, he's one of them. The dead one that's still living.
When you're in grad class, we have more knowledge, more analytical part. So, but sometimes, my experience, I've been teaching for more than 20 plus years. Undergraduate students are more enthusiastic and asking.
I think they are less afraid of being said, no, you are wrong on that idea. However, we can only go right if we are wrong sometimes, or not. We will be reading something that everyone was already done before. Thank you. I'm sorry to you.
So Fourier transform is one of the popular methods of ECG classification. So we had to use some power efficient routines. So we decided to go make our own AC application source integrated circuit for doing this. This is the basic morphological analysis. This is goes from bottom to up. So this is the your cure complex. Then you do Fourier transform, you get the spectrum. Then we have a little neural network that will say, which is what kind of arrhythmia we are having. So this is the wireless telemetry I was talking about. Now, for the top one is the current technology I talked about. So I will just skip that. Then this is the one we are aiming. Now, there's another problem with. Let me go back to the. So this is, let's say a patient is let's assume for minute we have the system. So a patient is having problem, and the patient's pacemaker communicated with the cell phone. Cell phone is communicating with the doctor or the hospital network. Now these days, anything can be hacked, right? So you never think about a pacemaker being hacked. That's the last thing you will think. But unfortunately, that is possible. University of Amherst, Massachusetts, they demonstrated that we can do it. And we in US, we even had a soap opera. I don't know what it's called. It's not sitcom. It's not a comedy thing. It's a TV serial.
No, not sitcom.
It's not, when you say sitcom, it's a comedy, right? It's not comedy. It's a TV serial. So very serious thing. So the bad guy was trying to kill the US vice president who has a pacemaker by hacking into the pacemaker. You get the wrong shot, the person will die. When Hollywood is thinking that means everybody is thinking about it, right?
If someone is thinking about it, it's already have been done before.
So now the point, all of a sudden, we are all excited. The pacemaker could communicate with the doctor and hospital network, and everything should be fine. No, there's something else is wrong. So now we had to think about encryption. Right? So that's, and again, I want you to understand the encryption. Actually, you don't need that for the pacemaker to work correctly. So now we are adding this encryption because bad guys won't get it. And so that's the typically it uses proprietary encryption, raises large security issues. So when you have proprietary encryption, there's another problem. So pacemaker, somebody with pacemaker has an issue. So emergency ambulance comes in. So the ambulance people cannot get into the pacemaker. If there was no encryption, the ambulance person could get into the pacemaker and do all the things. So this is kind of a bad situation. There has to be a standard so that only the medical people know, but the bad people won't get it, and that kind of thing. So this is the wireless telemetry. So I will skip. Now let's talk about the power usage. Powered by a small lithium ion battery. As I said, it cannot be recharged. It has used 10 to 10 years runtime. It's in the microwatt range. So the DSP and other communication go through take 29.8% of the total power. So target to reduce the computational power requirement at future workloads. So this is encryption we added, reliability we added, because those two you don't actually need for the pacemaker to work, just to make it secure and safe. So we have a goal of hardware software co-design. So future cardiac pacemaker trends: security and connectivity, reliability, improved battery life. So I kind of explained these things in the previous slides. So we'll keep moving. So this is our we are trying to we designed a new chip for the ASIC. This is our design. That's the encryption module. This is the processor. We have a FFT module. So now I'm going to how to optimize this signal. So far, the background. And as I said, I will not go into the circuit details. I will give you the overall idea, so you can read if you are interested later on. FFT fundamentals. Don't think I'm going to teach you this. No. So it is the basic stuff you can read. So we analyzed and we found out. So this is the basic ECG, and as we seen before, something is wrong. This waveform will be different, right? So we found out most of the computation is repeated. That means there will be something wrong here, but here everything will be same. So you don't have to keep on doing, again, mainly complex matrix multiplication, not matrix multiplication, complex number multiplication. So this is very power consuming operation. So if we identify lots of them are similar, so we, instead of keep on multiplying, if you can identify those repeated multiplication and store them in lookup table, so you eliminate all those things. So that's our key input into this. So FFT can be optimized by detecting and eliminating repeated calculations. this is again FFT routine. So what we did is, instead of going, we designed a chip that has that lookup table, and this is the original power consumption. This is the optimized power consumption, and then we went and designed our chip. As I said, these are the basics of the chip. Then okay, this is we designed our chip to detect 4 different arrhythmias. As I said, there are 94 of them. 12 of them are that occurs most commonly. This is even 4 most common ones. How did we pick this? I collaborated with our cardiologist. He said, okay, let's go with these 4. So these are the corresponding waveforms, and these are the ones that we did. And this is our other chip, and this is our final chip, and that this is energy per FFT. So we overall energy reduced by 38% using hash plus lookup method. If you are more interested in this results are published in IEEE transactions on ELS systems. So that paper, you will find all the details on that. Okay. So, now any questions? Right. Okay. So now let me talk about optimized encryption and reliability. I explained why we need AES, because there are bad. Now, cycle redundancy check, that's for reliability. So you typically we analyzed the steps to do AES and steps to do CRC, and we found out these are all basic logic blocks. There are several logic blocks that are similar for both. So we said, hey, why can't we share them? So that was our next thing. So these are the fundamentals of AES. But I am going to explain fundamentals of AES. This is the fundamentals of CRC. So our proposal was, well, we instead of AES and CRC never happens at the same time. So there are blocks for AES, there are blocks for CRC, and there are several similar blocks. Why don't we use them for both and design a new chip? That was our second part of research. So this is our second chip, and this is the power consumption and that much area saved. And this is we published in IEEE transactions on sustainable computing. So if you are interested, you can read on that. And that's conclusion. We designed and implemented an alpha low power FFT ASIC, and overall energy per FFT reduced by 38%. According to our calculation, battery life improved by approximately 8 months. So from 7 to 10 years should be 8 to 12 approximately, that kind of thing. So we designed and implemented a resource shared AEC CRC engine, 29% less area than standalone designs. And so these are the patents we got based on this research. We can, well, if you are into patents, we can read those patents. And finally, acknowledgement. This National Institute of Health gave me 2 grants to do this, and that is my student who did all these works, and he graduated. He's at Apple now, and I had thanked my good friend Manoj Pandey. Anytime I call, so it's been very helpful. So those are the my acknowledgement side.
Eugene,
thanks.
one of the things interesting that the results will show, because as you are reusing the blocks on CRC and AES, I think you probably actually increase the security, because now you cannot do. It's become probably become more difficult to do power analysis on the results to get it first sight, because now you don't. It's more complex to discover if you're ciphering or if you're doing just error correction code. Power analysis to extravate data from the pacemaker. So if you are an attacker,
AES is not always on, right? So AES.
No, that's right, because it's not always on.
Yeah.
If you probably the previous one, someone that likes to do that type of attack can verify, say, look, I know when they are using AES, so I know how to attack AES. I'm able to extravate data from that pacemaker, so I know if someone is sick or not. Because you decide you find a path to actually reuse the hardware blocks, become more complex for an attacker to
that's
discover
what you
if
said.
you are using
Yeah,
AES or CRC. You're just consuming because that is the difference on power. In power, it's gonna be it's not gonna be the same when you are full separate segregated circuits. So it's more complex. We end up probably increase the security part of that because you make more the power analysis more complex to do it. So it's more complicated for someone with the device to verify it. And why? Because for us it doesn't make sense, but he will say, the TV series trying to kill the vice president of the US actually is something that a government can use. And if it's cheap to discover, you can
use Lizy's.
no, because you can use it. Look, if I know the guy uses a chip peacemaker, I don't need to kill it. If I'm able to extrapolate data, I know his nervous or not because he's sampling. So it can be useful for diplomatic stuff. And what he did, if I'm not mistaken, okay, because it's only based on power analysis. Two segregated circuits, it has different power consumption. So if you are getting that data, now it's doing AES, now it's doing CRC. By reusing the block, you make this more complex because the block maybe now is always used, and now you are not able to really grasp what it's doing or just and try to use because you need to discover when he's doing AES to then try to discover what he's ciphering. And if you're not able to do that, or not maybe you are probably still able to do it. Okay. However, if you make more complex for him to discover that he's using AES, then it's much more complex to try to extraviate the data. That's quite a possibility to verify. Really interesting.
AES even otherwise is extremely hard to crack.
Yeah, the power analysis is the only thing because there are those researchers that and one of the things that they want to do is he's doing it. I know he's using AES. Okay. Oh, but because of the power consumption, I know that AES is running now. So now I can try. It's hard to crack, but not to extraviate data. That's the issue. And what I'm thinking, because of your description, you said it's probably that you make it even more complicated to extraviate data. I cannot still break the AES. I could extraviate data based on power consumption of how the AES was implemented, misimplementation usually. But because of you are reusing them part because of CRC, sorry the word, it's made more complicated because now I'm not able to understand that's relevant part. It's coming from where? I think it's AES. I'm gonna extraviate data. No, it's those binaries that I'm getting out. They are not anything related to the key that I want to get. They are actually the error correction code, so I'm not able to really grasp the data out. That's what I think was interesting because usually resource sharing is an issue, at least for microarchitecture. The computer we've been seeing recently the research on security is you have a shared component is bad because it's leaking information. However, in that case, by reusing the component, I'm actually put more noise in the system and getting extraviate the data more difficult than before. That was I don't know if it was originally your idea, but end up being, if not a plus, a bonus on the research, because then you can make it more complicated for people, for another people to get the data and do something. It's really interesting to think about it.
We think Lizy 2 times. So first, let's thank Professor.
Yes. Eugene, thank you for the call. And sorry for the sidebar.
They are, many of them are your students. Why are they so quiet? Is he like that? You don't ask any questions?
No, I told them if they ask, they'll die. They don't ask questions. They should have asked questions.
It's a Friday, right?
Yeah.
Yes. No worries.
It's when our mind goes to.
Yeah.
I don't get why it's important that the pacemaker be able to detect the kind of arrhythmia. Why do you have to do the signal processing inside the pacemaker?
Otherwise,
why is it in, what's the objective?
Okay, so a person implanted with arrhythmia might develop other kinds of arrhythmia. That's very highly likely. So we say one child, it may be type 2, type 3, different kinds of things. So we need to make sure that nothing else is going to happen. Did I answer your question?
Yeah.
See, that's why you interact with a cardiologist.
So Felipe sent you guys a message. He was really thankful for presenting here to us. He was not there here, but he's asking. He enjoyed a lot because we don't sometimes during our meeting we don't have time to see all those results and the ideas. So it was really good to grasp.
I can say it made me even more proud to be part of this group, because seeing these two bulks of two different bulks of research that sometimes they interact and sometimes they go.
Yeah, and I guess he did not mention we created this weightless neural network based arrhythmia detector on a plastic chip. So that's because of all of the collaboration.
Yeah,
because
they don't
for
know.
PESC-maker, for those who are sick, however, for the new Michael Jordans of the world, people want to monitor them all the time to get how to improve the athlete to the utmost. So researchers like we are doing now with PESC that allow you to put those devices in their body without compromising the training or or their playability itself are relevant for a multi-billionaire industry, to tell you the truth.
In this case, the multi-millionaire, but also is very important for public health. I couldn't forget all the time.
Once it's out, the one that you're gonna buy is gonna be Chicago Bulls. And Wizards is gonna also Golden State's gonna use it because money talks.
But, I remember a lady with the two daughters that her pacemaker had a finished battery, and she was really tired, and they were on TV talking about the service that was interrupted, and she needed to change. I couldn't help thinking about her all the time. On the TV.
This week or last week? I saw that.
You saw that. So it was.
But again, thank you, Eugene. Thank you, Lizy, for the talk and
Let me tell you, on behalf of C and myself, thank you for having us here.
Oh, it's a pleasure.
Pleasure.
It's always a pleasure, and be able to have these broader discussions. I think for the students it's great because they see that our research doesn't stop when we do the paper. We have the experience, and maybe when we talk, we find a different paths that can be evaluated and move on. That's something that really, I think, the most important part of when we have these talks in the university is for give them this concept. You're not gonna, because sometimes I'm a genius. I'm gonna go to my office and produce a lot of papers, and I'm out. Research is not that. It's a teamwork. It's collaboration. It's I've done until this point. Someone else gonna pick up, and that's how our field lives actually. So when we see this possibility, we do the talk, and both of you actually did this more than I've seen in different occasions. Not only I'm interrupting or not, but have this conversation with the audience is really good because show them that we should not be afraid of asking questions. Maybe I don't know the answer, but not knowing the answer is good because it's something to work on. And both of you, when you're talking, make that. You not only by saying, but your posture, invite the audience to talk and to communicate. Thank you a lot. It was not only for them, but also for me. It was a awesome class. No, okay.
Thank you. Thank you.
Eu corto essa parte. I usually cut this.